So this begins the last unit. This is all the final exam material. Don't ask me when the final is. I'll send you a form. We'll figure it out. It's on that final exam schedule. You don't have to be a rocket scientist to figure it out. But, and so effectively anything for that exam, whose date I will endeavor to show everybody again for the latecomers, Monday, 11/17. Don't have to thank me. It's all service that we provide. So we will begin from there. And yes, to that end, if I'm feeling frisky, probably not tomorrow, maybe tomorrow, I'll try to do one of those review recordings again. But I do have to go over it. You can't have it. You foolishly enrolled in micro. I try to tell them, the students, I don't want to have in the class, but I can't make that call. So if you see a note from the registrar saying he doesn't want you, it's me. I endeavor to have fun with diseases. Oh, all right. I try to ignore all these messages, but we will begin. So this is the PowerPoint that we will be using very much for this, our 11A, B, and C. B has a lot of the sophisticated physiology on it. That's what it's dedicated to. C is all about neurotransmitters. Very important. And this is really the anatomy part of the program. So I do not know, but I think it's important. I do not know, understanding the setup. There are two basic control systems that are involved. And so in our bodies, there's one that does things extraordinarily rapidly. That's the nervous system. The one that is still very rapid, albeit slower, is the endocrine system. We're going from fractions, microseconds here in the nervous system to seconds, minutes, hours, days, etc., or longer when we're talking about the endocrine system. So the endocrine system is something we do not deal with, really maybe a skosh toward the very end when we talk about the autonomic nervous system. You're going to see the construct in a second. But effectively, this is the one we dedicate the rest of this term to understanding the nervous system, going over some of the stuff about the brain, maybe accenting a little bit more, less of the anatomy and a little bit more of the physiology of the brain, and sort of rounding it up with the autonomic nervous system. That is the plan of attack. So on we go. Sensory input. Okay, so what it does. And basically, there's incoming sensory information. There's outgoing motor output. So you're going to see the terms a lot. This is effector organs going to muscles and glands. So the terms that you're going to get used to, if we haven't talked about it already, when we talk about sensory, anything that's incoming, we use the term afferent. Capital A, F-F-E-R-E-N-T. And for outgoing, we talk about efferent. And the derivation of efferent is from effectors. Why am I accenting those, as I do all the time? If you say afferent and efferent, it's a little hard to distinguish between the two. So when you're in science and in medicine or any of those areas, you always make sure to leave, because errors may create big problems. So there's afferent and efferent. So we have sensory information, incoming signals, efferent information or motor output or effector output, outgoing signals, and the rest of it is integration. The vast majority of the nerves, we're talking about 98% of the nerves, maybe more, are all about integration. It's less about what's coming in. It's less about how we react to it. It's all about the construct of being able to do things. It's a microcosm of how we interact with our lives. Okay, we take in all the things we're seeing. Okay, all the things you do and you don't even think about doing. He walks in this room, what's the first thing you notice? They got the heat on. So off comes the jacket. Maybe you have, and around here you learn to dress in layers right away. Okay, because you never can tell what they're going to have. Just wait. The AC will be banging away right in the middle of February. I promise you. Same room, same station. So sensory, motor, all integrated. Yeah, I see it. I want it. I'm going to grab it. Okay. So this is the anatomical construct. It's very simple. Very first lab, you learn about those body cavities. The dorsal body cavity, very tiny, only has two things in it: the brain and the spinal cord. That is your central nervous system, period. That's the contents of the dorsal body cavity. Anything that sticks out of there, whether it's a cranial nerve or a peripheral nerve, and how many of those you went over, I do not know in lab. You did cranial nerves, correct? Did you also do peripheral nerves? Not so much musculocutaneous, femoral, obturator, not ringing a bell. Sciatic? No, okay. The reason I'm asking you is since Dr. Robbins is going to handle, will again have all the AP2 labs, except thankfully you'll have a whole term to deal with them. He'll know where to start. But I have to get in touch with whoever's doing the lectures and say kind of, where I end, because they can start. They can pick it up from there. Nevertheless, so anything that protrudes, cranial nerves and spinal nerves are what protrude. They become part of the peripheral nervous system, mainly of nerves that extend from the brain and the spinal cord. Here they are, spinal nerves. And spinal nerves are not just outgoing. We talk about nerves. They're both motor and sensory, and most of the time they are a combination. Well, you did the cranial nerves. There's only 2 of them that are purely sensory. You remember which 2? You don't remember which 2. The first 2, olfactory and optic. The only 2 nerves that are purely sensory. The other 10 cranial nerves, okay, which I'll be happy to name for you if you wish, but you don't have to know them. For me, that's a lab thing, are all mixed to some degree. Basically, they're combinations of motor and sensory. We used to think that the vestibulocochlear, your hearing and balance nerve, is purely sensory. But when you're hearing, like you go to a concert and hear loud things, there's an adaptation. There's 2 little muscles. Do you remember them? Tympani and the stapedius muscles that are in you guys didn't do ear anatomy yet. Okay. And they adjust the tension on those 3 little bones, the hammer, anvil, and stirrups, incus, malleus, and stapes. Don't know any of this. And adjust for it. So everything we talk about nerves, they're pretty much mixed nerves with limited exceptions. Wah, here they are. That's lab. Don't do it. Don't care about it. But it's very, 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 very interesting in the construction of it. We are dealing today with this whole chapter deals more about the microscopic and physiological aspects. We do most of the anatomy today, maybe a little bit more on Friday, and then we delve into the physiology. The peripheral nervous system, which we're not touching per se, other than this, the autonomic or PNS, again, incoming signals that come from your body, bones, muscles, joints, etc., and visceral, which means it comes from the organs. Sensory, and plus it has outgoing division, transmitting, okay, to whether it's muscles or glands, and you'll see, the construct is easier. So this gives you an idea what somatic is. Again, I'm not going to ask you about this. Okay, fibers conduct impulses mostly to skeletal muscle, and their voluntary control. We talked about that already with muscles. This is repetitive. This is the one that we're going to spend a lot of time with, called the autonomic. Again, you could use the term automatic. By definition, it is referred to as it's sort of the motor division that's going. It's basically a motor division rather than a true sensory division. So obviously, it has to utilize sensory impulses. So visceral motor nerves, nerves going to organs and telling them what to do. And down the road, when we get to it, the linchpin for most of this is called the vagus nerve. Smooth muscle, cardiac, there's other nerves. Smooth muscle, cardiac muscle, and glands. It's involuntary. It's got 2 divisions, sympathetic, which you're going to come to learn as action, parasympathetic, which is what you're using now. We call it the rest and digest. And they basically are a beautiful demonstration of homeostasis. Okay, and we are constantly keeping the internal stuff in balance. We're not doing that in this chapter. So I'm setting the framework. They always use this construct. Maybe you saw it before, maybe not. Our focus point for now, again, is really just going to be generically how nerves work more than anything else, and maybe looking at a few specifics in certain areas, because there's anatomical differences in the areas, and there are different kinds of nerves. And this is information you're going to need to know to sort of set the path for you, understanding what things go on when you get into AP2. And that's a lot of what AP1 is, sort of giving you the anatomy and basic physiology, and then be able to look at it at the systems you explore in that area. So peripheral nervous system, cranial and spinal nerves, yeah, communication lines, I'll buy that. Incoming, outgoing, afferent and efferent. They either go to your body or your glands. Basically, that's what this means. And the ones that are outgoing, sympathetic and parasympathetic. You'll see this again and again. And no, I'm not going to, I will make sure that whatever the questions are, I'll be very specific about those content areas of this basic stuff. Before you get to nerves, something you probably did, I'm going to get the second lab session when you start to learn about lining tissues and connective tissues, right? All those epithelial, loose areolar, dense irregular. Is that all ringing a bell? Elastic. I love that. I'm a nut for that type of stuff. In the nervous system, guess what? They have whole new kind of connective tissue. See, the nervous system is so important, it has like its own staff. For the other, most of the rest of your body has to deal with the same staff, just different amounts in different places. If you want to think of it in that construct, that way. I'm trying to think of something creative that'll catch your attention. I realize it is early in the morning to put up with my dulcet tones. Better there. That's right. Fortunately, unlike my wife, you're not allowed to look at me and go, "Shut up, Lou." See, occasionally someone smiles. These are called glial cells, neuroglia. Glial means glue. They are the glue of the nervous system. Their whole job is to support, nourish, embrace, guide, direct, do the stuff to keep the nervous system working properly. So nervous tissue consists of the nerve cells. We're not going to do those yet. They're more or less fairly generic. Okay? They have really, it's a more generic. If you think of something that's so complicated to understand, the best way to try to understand something that's complicated is to simplify it. The neuroglial cells are really tiny, and because the nerves are so delicate, they wrap around them. There are only 6. 4 of them are in the central nervous system. God, I have to get 4 of them are in the central nervous system. 2 are in the, we always use the abbreviation CNS and DNS. They have similar roles, okay? You have astrocytes, have oligodendrocytes. Going the same way I have it up there. Okay, you have ependymal cells. And you have microglia. Here, sort of the mate to this, I'll get one right so it's better. It's called a Schwann cell. No relation to frozen goods that are delivered around here. And maybe, and we'll draw sort of a squiggly line to that, something called a satellite cell. Those are the ones in the CNS. And this one, we're not quite sure if it's world, never happened. Okay? Those are the 4 cells. And so, yeah, it's incumbent upon you. I got to use the word incumbent in a sentence. Okay, it is incumbent upon you to be able to know which is which and which system they go to. Got it? Thinking of a test question. Okay. Typical test question. By this point in your academic careers, you should be discerning from already knowing what my questions are like. Which one of these, what cell does blank in the peripheral nervous system? Immediately, you have 2 answers. And you go out and search for that answer. Yes, ma'am. The 2 in blue. Pardon me? Yeah, PNS. I know. I have another black one here. I never know if they have tips or not. So these are the supportive cells. These are the excitable cells. Voila. Astrocytes, the most important, the most abundant, the ones that do the most stuff. microglia, ependymal, and oligodendrocytes. Coming up. Astrocytes. You've heard me talk about it maybe a little bit in passing. There's a thing called the blood-brain barrier. It has to do with the fact that only things that are effectively fat soluble and sufficiently small. This is when we get back to this water and fat soluble stuff talked about forever, since roughly day 1 or day 2 around here. And what it's about, okay, is something called the blood-brain barrier. The capillaries are unique in that area. That's where the exchange takes place. The capillaries have an abundance of tight junctions. An abundance means water-based things can't get through. So they have to be fat, get through, and they can't get through directly into the nerves. They have to pass their way through the astrocytes for like an additional layer of protection. You will see it soon. Highly branched. They cover a lot of area. They cling to the neurons. They cling where the synapses are, okay, and the capillaries. So they support them, hold them intact. You have tons of nerves, but they're highly, highly organized. An amazing amount of nerves that are very, very tiny, and they're held very specifically. This is what I was talking about. To get nutrients in and waste products out, or to get medications in, it has to be able to make its way literally through the membranes of the astrocytes. It's got to get through these unique capillaries that water-based things can't get through, and then it has to get through the astrocytes. Growth and development. Like you're born with all of your nerves, everybody. All of those neurons, the nerve cells are there. How they develop is remarkable. The whole development of being able to understand, look at the events from a baby when it's born, which is effectively helpless, okay, to what we are today. Okay, look at all those wonderful landmarks. You know, when the baby can start to hold its head up, when they can start to crawl, when they can start to walk. You know, pictures forever. Okay, those are so important. And it all has to do with this guiding them, where they're going to move to, making sure the chemical environment is kept appropriate so it's homeostatic in that regard. It's impacted, okay, by other nerves firing and the chemicals they release, which are neurotransmitters. So they influence that function, and they're part of information processing. They have a big role. This is kind of the way to understand. The yellowish here is a nerve. The red will be a capillary. Again, those capillaries are extraordinarily rare because water-soluble products can't get through. So effectively, if a nutrient escapes here, or oxygen, it has to travel to get to the nerve. It comes out of the capillary, let's say here, goes along the membrane or through the fatty portion in here, and then goes into the nerve that way. And the waste products take the same path in reverse. Nutrients in, waste products out, oxygen in, carbon dioxide out. Got it? So they're an integral part of this arrangement. You can see how abundant they are, and it's really a useful little, illustration of how much coverage they are, not only on the capillary itself, the tiny blood vessel, but also on the nerve itself. They have their own sort of white blood cell network. If white blood cells are in your brain, you've got a major problem. These are analogous, but they're sort of like little sweepers. White blood cells generally have multiple tentacle-like projections with lots of lines. They look you'll see what they look like. They're small cells with thorny is a good way to describe it. And they're in contact. And what they're doing is they're picking up areas where there might be small injuries, debris, like any other tissue. Some aspects are being replaced, typically not of the nerves, mostly of the glial cells. So they can transform basically into a macrophage type of a cell. They're much, much smaller. Hence the name micro, for very tiny glial cells. And phagocytize, gobble up if microorganisms get there, debris from the nervous system. And the reason there's debris, There's a tremendous amount of processing involved in making neurotransmitters, releasing them. We saw that at the neuromuscular junction. What happens to that stuff that diffuses out of there? Something's got to gobble it up. That's a micron. Getting the idea? Here it is. And you see what white blood cells look like microscopically, and that's more about the immune system when you study it, or the blood when you study it, and that's an AP2. They're very, very similar in their appearance, albeit quite a bit larger. And so they're there. Ependymal cells, very unique. We're going to spend a fair amount of time. I'm sure you did. When you looked at the brain, you talked about the ventricles, lateral ventricle, third ventricle, fourth ventricle, right? Those fluid-filled areas, you saw all the illustrations. Happy days. They're filled with what? Cerebrospinal fluid. The cerebrospinal fluid comes from your plasma. It's not plasma. It's extracted or a filtrate of plasma with a lot of the same ingredients in different proportions, and it's finalized in a very unique area, which you're going to see when, and I'll review it again in the brain. Maybe you recall what the name was called, the choroid plexus. Is that ringing a bell? See, we have a bell ringer. Ding, ding. I should get a little bell. But my dog would come over, figure it's snack time. Choroid plexus. So the choroid plexus basically is a loop of capillaries, and it's covered in, that's right, we're finally getting to the point of all this, an ependymal cell. They're a lining cell from squamous to columnar, no big deal. And because cerebrospinal fluid is flowing, it has cilia, just like you have in your respiratory area or in your digestive area. You have things that move stuff around. Remember those pseudostratified ciliated columnar epithelia of the respiratory tract that you're going to get to? You might remember them from looking at those wonderful lining cells. Here they are. These are also ciliated cells. They line the cavities of the brain and the spinal. Those are those ventricles, and a permeable, which means it's a crossable barrier between the cerebrospinal fluid and the tissue fluid bathing the central nervous system. So they're all part of this interesting way of getting cerebrospinal fluid. And cerebrospinal fluid is very much different. When we see things in there, and that's why we do things, and perhaps you learned about it. You did spinal cord anatomy, correct? Right? You talked about the chorda equina, the filum terminale, cervical. You didn't do cervical, brachial. You did that stuff. Cervical, thoracic, lumbar. Gotcha. Those vertebrae bones, they have a reason they're protecting the spinal cord. And okay, what's effectively, did you talk about why we can do a spinal tap and where we can do a spinal tap? We'll cover that. It's okay. Good news. It's coming in chapter 12. You don't have to thank me. It's all part of the service. That's another wild movie that they're going to reboot. Well, this is Spinal Tap. It's about a rock band that was aging, and they're older still. Did anybody see a movie called Best in Show? Yes. Hysterical. Two Left Feet. The same group who did this. Did you ever see a TV show that was played on Comedy Channel called Schitt's Creek? Same people. Okay, they're all the old Second City TV people. Brilliant. Absolutely brilliant. And Best in Show is a parody, sort of what they call a mockumentary about like dog shows, particularly the Westminster show, which was in Madison Square Garden, New York City forever, and it was appointment TV. Just to hear this stuff. They do a mockumentary about it. It's absolutely unbelievably funny. And the word I would describe, to be kind, would be crude. And you just go, you'll find it. Go find it. It'll be on Pluto TV or one of those, Tubi TV. You'll find it. You don't have to pay for it. So, effectively, this is the fluid that's bathing the area. This is what they look like. This would be one of the ventricles. And so that's movement. Because the cerebrospinal fluid, as you will learn, we make about a pint a day, and we have to get rid of about a pint a day. And there's little siphons that are in those aforementioned ventricle areas and in the meningeal areas. The meninges are the covering. This is not the chapter, but the next chapter where we learn about those coverings that are on the brain. Meninges are from which meningitis the term evolves from, pronounced depending on who pronounces it. Lastly, the oligodendrocytes. Your brain consists, and I knew you had to do this in lab because you saw the sheep's brain. You have two types of matter. You have gray matter and white matter. What makes the white matter white is the fact that it's covered in a material. It's basically those transmission lines. Okay, all the fibers that are sending information out and bringing information in are typically, until they get to the processing plant, covered in white matter called myelin. Myelin is a very unique material that's made of protein and fat. So it's strong, yet it insulates. This oligodendrocyte is how the myelin is really, its cell membrane is effectively the myelin that's found in the central nervous system. Its cousin, the Schwann cell, is the one that's in the peripheral nervous system. That is an extraordinarily important distinction. You will see that shortly. So forming insulating myelin sheaths. If you want to know about a demyelinating disease that you have to be very worried of because it's more common than you think, and ladies, it's probably 4 out of 5, at least in my experience, ladies, as most autoimmune diseases are, it's called MS, or multiple sclerosis. They get sclerosis or hardened areas in the myelin sheath, and it deteriorates. If you're going into a clinical field, you will see people with MS, and there's not a lot of good treatment. So here you are. These are nerve. The yellow is the nerve. And so this is such a unique, these cells don't just wrap around one nerve. You're going to see that's part of the difference that you will see when you get to the Schwann cell anatomically. They wrap around multiple nerves because there's not a whole lot of space up here. So those nerves have to be held relatively tightly. So you have multiple nerves in a relatively tight package surrounded by these membranes of these very unique cells called oligodendrocytes. Nerves, take a nerve in your extremity, what we call a peripheral nerve. Anywhere else in your body, they're freely movable. You can move those things around easily, comparatively. They're not really tethered or attached to stuff. Okay, you have room. You inherently have space that's maybe occupied by fat or other blood vessels or other kinds of structural, but they're not held in place. Here, they have to be held in place. That's the job of a oligodendrocyte. And you'll see the way the transmission goes. When we transmit signals, it goes along these gaps. They are now called myelin sheath gaps. That is not necessarily a name that you will hear a lot of from me, because it's another one of the things, I don't know why they changed the name, but sometimes they feel compelled, because I love saying the name. Those gaps And again, depending on where you're working, this is who's teaching you. They're going to be calling them nodes of, named after a French scientist, physician, whatever. Ranvier. Or you could say Ranvier. It's like my son used to live in North Versailles, but he used to say Versailles. Those living in France. Ranvier. Ranvier, everybody. Love that. And you'll see them not only in this system, the central nervous system, but also in the peripheral nervous system when we look at the Schwann cell. So here they are. In the peripheral nervous system, we have satellite cells. Cells of the nerve themselves have a different name. You might have seen me mention it in passing before when we were talking about the neuromuscular junction. We don't call the nucleus of the nerve a nucleus, because I'm sure you learned in the lab that we use the term nuclei, like basal nuclei, like red nucleus, like the nucleus of the fourth cranial nerve, whatever. So we refer to these, those are aggregations of cell bodies. So the name that we give to the nucleus of nerves per se, if we're looking at them individually, we will use the term cell body. Sometimes you'll see the term perikaryon, peri for around, karyon for the core or the kernel, or even something called the soma, S-O-M-A, for the body of the nerve. I've seen them all. The reason I mention them to you, I'll make it clear what it is from a test perspective, but, thankfully, after the end of this year, you're done with me. And most people, you don't see me again unless you come back and want to visit with me. I had 2 students who are juniors now I hadn't seen since they finished first year. Drop by. Right in the middle of lunch, of course. I'm eating. Get out of here. So, because other people may use a different terminology. And it's good that you know it going in. I'm trying to prepare you. So, okay, when it says function similar, those are code words again for we don't know. Similar maybe has been associated with, if it's not a simple declarative statement, particularly in science, it's short for we don't know. And for years they didn't know. Yes, it probably has similar role to the astrocyte. That would be concurred upon. But these bad boys we know about. Schwann cells, neurolemmacytes, okay? Another name for it. The neurolemma, again, like a sarcolemma when we're talking about muscle, is the membrane. So they surround the membrane. Is one way you might remember if somebody would tell you neurolemmacytes, I'll tell you Schwann cells. Surrounds peripheral nerve fibers and forms myelin sheaths in the thicker fibers. Similar, almost an identical function. The oligodendrocytes have some organizational because they're grabbing as many as like 60 nerves themselves at one time. Very significant to nerve repair. This is additional information that you certainly do not need to know. It's because of the Schwann cells. We're going to get to it. I'll jump ahead. Okay. This is, for instance, this would be a sensory nerve. Okay. And there you have the cell body. Here you have the satellite cells around it. And you can see the way the Schwann cells are wrapped individually. And again, the signal is sort of jumping between these nodes. All done with that. The point I wanted to make is regenerative power, which you will not cover. You may cover when you do peripheral nerve function in AP2, but I won't be there. So effectively this, imagine if this was sharply severed. Nerves die when the cell body is damaged. The transmission lines, typically referred to, as you will see shortly, as axons, AXONS, can grow back together. That's the reason when you hear terrible stories about somebody who has had an industrial accident and they were caught and something literally cut right through their arm or their leg, and they were able, or their finger, and they were able to put it back on, and it took. They were able to replant that appendage. The reason for that is nerves can knit back together. Slowly, but they can knit back together. I mean, I've seen that in surgical cases when you operate on somebody, you're going to cut nerves. I've had people who came back to me a year later. That part was numb when you operated on it. The operation worked, but I didn't like the fact I couldn't feel it. And a year later, they come back. It's magic. I can feel it again. And it ain't magic. It just takes time. That's something that you don't have to know about for this class. I teach my advanced class. It's called nerve growth factor. And we didn't even know about it when I was in school. A lot of these growth factors, things that impact wound healing clinics and areas like that, very sophisticated stuff, are science that probably has developed over the last 40 to 50 years, knowing more about it consistently. So that's why I wanted to share that with you. That's not testable stuff. It's trying to understand how these things work. So they play an important role in regeneration. That's the point. That's the construct. So why is this? You'll see that this is a special construct that we're going to get to at the end of this chapter. Probably won't get to it today, called a unipolar nerve. Okay. but it has peripheral nerves, have Schwann cells intermittently. This would be where it's receiving a sensory signal, and this end would be conducting it back to the spinal cord. And this is something that you're going to see when we look at a little bit of spinal anatomy called the dorsal root ganglia. We'll get there. The interesting, and why I want to make a point about that, because despite me wanting it to be otherwise, unfortunately, I have to teach micro to some of you. And that's where, are you ready? A virus that once you have, you can never get rid of, called herpes, hangs out, and why it can be recurrent. That's where it hangs out. Sensory nerve cell bodies, known as dorsal root ganglia. And most of you have been exposed to herpes. Herpes type 1 is everywhere. So the nerves themselves. So we'll look at this and try to get through some of the materia. Are structural units of the nervous system. I'll buy that. Highly specialized, large, long. The length of one of these tails, these axons, can easily approach a meter in length. If you take somebody who's 6 feet tall, think of it. It's a 2-nerve circuit for them to point their toe someplace or move their foot. One nerve goes to the lumbar sacral area of the spinal cord from the brain. The other one has to get down to that toe somehow. 2-nerve circuit. So unlike muscles, which probably the longest one, again, the sartorius, not a question that's going to be on the exam, which is roughly a foot long, these are 3 times, can be 3 times. So they last your lifetime. If they don't, you're in trouble. They're amitotic. We don't make any more. Good news and bad news, just like muscles. Once they're damaged, with muscles, we can make them stronger. We can work what we have. With nerves, once they're damaged, as long as they're damaged again, if we go back, when the damage occurs in the cell body, they're going to deteriorate. There's nothing you can do. You'll hear me, we go into a unit about stroke a little bit here, which are known as cerebrovascular accidents. A cerebrovascular accident is kind of like is a lack of blood supply, typically, or an interruption in the true circulation going there. Brain cells die. Period. There's no such thing. Oh, grandma had a light stroke, drives me crazy. There's a thing you're going to hear about in this class called the TIA. That's often misinterpreted or the doctor said she had a light stroke because they're trying to explain it to you, but she's all better. If there was a stroke, there is damage. Brain cells die. Whether or not they impair you is totally a different question. If you have a heart attack, heart muscle cells die. Whether you even know that you had it, whether it is life-threatening and to what degree it impairs you, is a totally different question. A lot of times, doctors and nurses and people who take care of other people talk to people to try to explain to them, and you can't go into that degree of technical stuff. I understand that. There's a fine line between dismissively speaking to somebody and informing somebody. You can't inform somebody who doesn't want to know about it or the material is too complex. But you don't want to be dismissive, because if it's something that's potentially serious, they have to know about it. It's your job. Years ago, when I was a kid, bless you, the doctors, okay, somebody was really, okay, we're going to get you taken care of. If they have pancreatic cancer, they're going to die. I'm sorry. I mean, but that was acceptable then because it was a different world. Legally speaking, it's a big term. Many of you will learn if you're going into a clinical field, you have to be to some extent transparent. I'm fond of saying, and you probably have heard me say it, nobody likes surprises. Not like that. Maybe your birthday. Bless you. God, you might be allergic to me. It's by my cat. So that's the bad news. The good news, gotta be good news, they don't get cancer. What about brain cancer? All those glial cells, that's the brain cancer. Those are connective tissue cells that can get cancers, not the nerve itself. When you'll hear about an optic nerve glioma. 90% of all brain tumors are benign. You'll hear about a malignant schwannoma. Those are glial cell tumors. A neuroma, a relatively common diagnosis, is really a nerve and fibrous tumor, but again, it's around the lining. The union between the fibrous lining, whether it's myelinated or not. That's called a neuroma. So, again, few exceptions. They're very, very rare. I can't recall them off the top of my head. It's look upable. And you have to have oxygen and you have to have glucose. Your brain only works on glucose. That's why, and you should learn this when you're talking about diabetes, okay, that the thing, high blood sugar will kill you in diabetes slowly. Low blood sugar will kill you rapidly, because your brain will stop working if your sugar plummets. That's the real danger with insulin-dependent diabetics. They take their insulin and they forget to eat, or they decide they're going to eat at work and they bottom out and they lose consciousness and they're driving the car right into a tree. Now, I've had patients where that has happened. One where he didn't take his insulin in the morning, figured he only had 50-minute drive to work. For whatever reason, the next thing he knew, he said, I remember parking at work, thankfully. The next thing he knew, he woke up in the hospital. And just like in the movies, they give you a shot of sugar and where am I? What happened? Perfectly normal. That's because of glucose. Oxygen is obvious. Okay? Oxygen is obvious. So all have a cell body, and one or more of these processes, those are the things that extend. So the cell body, again, perikaryon or soma, that's where everything's shaped. We make everything there. They make the proteins, they make the membranes, they make all of the chemicals that are needed for a nerve to function or to conduct business properly. A lot of them are pigmented and they're made in the rough endoplasmic reticulum. That's where protein and protein-like substances are made. When they say chromatophilic, and this is pronounced Nissl bodies, typically we see pigmentation, that red nucleus in the midbrain, the substantia nigra, the black stuff. They will have a nucleus, they'll have a nucleolus, they will have pigments. Typically, the plasma membrane is part of the receptive area and receive inputs. We're going to show you the typical nerve construct. And again, what we see here consistently when we start looking at these cell bodies, that's why we don't use the term nucleus. So nuclei now, by definition, are clusters of cell bodies in the central nervous system, while clusters of cell bodies in the peripheral nervous system are called ganglia. It's a confusing term because I've removed ganglia, which happen to be a soft tissue mass that's associated with an outpouching of a joint. But so again, very often you have to be specific because we have a tendency to use terms more than once. It's like cervical cancer. Well, that's in the uterine cervix. Well, there's a cervix up here. Couldn't have cancer up there. Cervix just means neck. Avoid confusion. We'll leave it there because it's going to take me a little while to go through all these processes. Thank you. We are done.